So solving logarithmic equations, you saw already, as I said, when we solve exponential equations using logarithms, but these are, most of these, at least, I think all of these, are logarithmic equations. And there's a few different types. Again, subtle differences make the questions different, but none of them are all that hard. I'll be upfront with you. This stuff is not like some of the other solving that we've done. But again, there's enough different kinds that, you know, people can get them mixed up. So you do want to have some sense of the different kinds of questions. Before we even get to that, I want to talk about restrictions, because much like rational equations and rational inequalities and all that stuff where we talked about restrictions, same goes here. Okay? There are restrictions involved. So we're going to start with two things. We're going to have log base a of b to the c. So this is a logarithm, obviously. It's got three things. Oh, that's not right. Equals c. It's got three places where there's a number could go. And depending on where you put the numbers and where you put the unknown, you would solve this differently, which is not really what we're talking about right now, right? But all of these numbers could change. Yeah. Yeah, we haven't really done anything yet. I don't know what you'd be asking a question about. Oh, I see. Okay. Then I'm going to rewrite this in exponential form because we're going to talk about both. Remember, the base stays the same. So log base a is exponent or a power with a base of a. And the c and the b flip. So this is the same thing rewritten in logarithmic form and exponential form. How are we going to start to explore restrictions? With a sketch of the graph. What does the graph of just a random basic logarithm look like? Again, this is, to me, you should know the basic of a logarithmic graph as well as an exponential graph, of course. And we're not doing a lot of transformations or a lot of graphing. There's none on the quiz, but we should know a general idea of what it looks like because it helps inform us about how the function works, like in terms of restrictions. So the logarithm looks like this. And exponential, depending on the base, looks like this. It won't matter if I have a base. It won't matter in this case if it's increasing or decreasing. So it could go the other direction. It'll be the same idea. What's this logarithmic graph?
X can be anything greater than 0.
Good. What's the range? Yes. What about the domain and range of the exponential function? Yeah. And then the range? Very good. What do you notice about these two? One is the inverse of the other, so the domain and range flip. Did you notice that? It's not a coincidence. If you remember doing inverse in grade 11, that happens every time. When you have a graph and you take its inverse, the domain and range like trade places. Okay, so it makes sense that this would be the case. Now here's the tricky part. Now folks, this is like, you know, if you don't fully follow the next couple of minutes, it's not the end of the world. What you need to know in the end is where the restrictions are in all of these kinds of questions. So we're just exploring to try to figure this out. What does x correspond to? X in this top graph, what does it correspond to here? Oh, I should have written this out. So this is a graph of y equals log base a of x, and this is y equals a to the x, some value a to the x, and this is y equals some log some base a of x. So now, what does x in this graph correspond to in our expression, our statement over here? Sima? B. X is B. Right. Our X is our B. So what does that tell us about a logarithmic function? Yeah, so our restriction is B has to be greater than 0. Not greater than or equal to, greater than 0. And what does X correspond to from the exponential graph? B still, right? Because we rewrote it, so it's the same thing. So, sorry, Y in this case, not X. Y is our B. See that? And Y has the same restriction. Y is only greater than 0 based on the function. When I look at this graph and I see on this graph X never goes over here, that's telling me about this function. That means B cannot be negative. Doesn't exist in the graph, can't exist here. Does that make sense? That's a pretty important, subtle idea, though, that I can look at the properties of the graph and it can help inform me about this actual operation or function, right? And then same thing here. The Y value never goes below 0. Well, B is my Y in this case, and C is my X. Okay? C can be X can be anything here. Y can be anything here, so there's no restriction on C, and that makes sense. If I take some power, like 2, I can throw any exponent I want at it. I can 5, -10, 1/2, whatever I want. It will work. And then again, it makes sense that it'll never equal 0, because if I go 2 to the something, will it equal 0? Okay, so this also all kind of fits with our understanding of these things. Yes, Isaac. So if you shift it, well, we'll see that actually. We'll come back to that when we get there. We'll see ones that are like that. Okay, how's that? We'll talk about it when we get there. There's another restriction, though. It's not as obvious, I guess, from the sketch, although if you look back to the very first day of this unit, it's related to something we talked about that day. X cannot equal 0. We kind of just talked about that, but that's right. Yeah. That's not the other part, though. So I just said, so we said B has to be positive. It's got to be greater than 0. C can be anything, no restrictions. What's left? A. Is there a restriction on A? A is greater than 0. We talked about it here in exponents. Do you remember? You can't have a graph of y equals -2 to the x, because it flips back and forth, positive and negative. It does not look anything like that. And get your calculator out. If you have the fancy button that you can change base, let's do this. I think we talked about this already. This came up. Somebody asked about this maybe. -2 cubed is -8. So how would I rewrite this in logarithmic form? Base stays the same. And then the other parts flip. Punch it in on your calculator. Log, if you can, log base -2 of -8. And hit equals and tell me what you get. In other words, you should get 3, isn't that right? In our heads, this relationship makes sense. What did you get on your calculator? Error. So the logarithmic function will not process, even if it seems to make sense to us. The function doesn't process with a negative base. So A must also be greater than 0. It can't equal 0. It's got to be greater than 0. Yeah.
Is that just because it can't be a log? Because it keeps...
Yeah. Because it would, again, like flip back and forth, like it doesn't make any sense. So there's my 2 restrictions. And remember when I said there's all different kinds. The very basic questions. Yeah?
Like mathematically, isn't that possible that when I do it though? Like, couldn't you technically still draw it even if it's like crisscrossy?
I don't think it would. It wouldn't map out as a continuous function. Continuous is a definition you'll learn about in calculus. And so it looks like it would just flip back and forth, but it wouldn't be like straight lines drawn between. Yeah, and it would like jump from one to the like, so it wouldn't have any natural behavior, and there isn't a graph of it. So it's definitely not this function that we can graph. It would be something else. So in some there may be areas like disciplines in the world that would allow it, but I mean, as you can see, even when it makes sense, calculators throw an error. So yeah, why wouldn't the calculator be able to solve that? But yeah. Okay, so take a look at B and C for now. Just look at them. Again, remember when we did this, log base A of B equals C. For this one, X is the A. For this one, X is the B. And then we've already done ones where X is the C, log base 2 of 8 equals X, which is really just a different way of evaluating. And for all of these, the way that we've been solving them, like this one, and the way we will solve the other ones is by rewriting an exponential form. So you have sort of three possibilities for these. These are simple logarithmic equations, not very interesting, okay? But they do, obviously, they are going to come up for us a little bit. And I like to think of it as like, where's the X? Where do you put the X? That makes them all a little bit different. But ultimately, when I rewrite in exponential form, whatever I get next, I have to think of how to solve. So no matter what kind you're talking about, these questions, the first step's always going to be the same. So the base stays the same. This is 3 squared equals x plus 1. And this is a brutally easy equation to solve. 9 equals x plus 1. Subtract 1 from both sides, and I get x equals 8. But remember our restrictions. Isaac, would you agree that this is a shift to the left 1? This is what you were asking about. So what you are saying is if I shift left 1, the graph's going to look like this. Right. Right, but it looks like this, so you have a bunch of negative values. But all we do is we say x plus 1 must be greater than 0. The argument of the log, whatever it is, and then I'm going to solve that. X is greater than negative 1. So even if you have a shift, it's the argument of the log that can't equal 0, which means it's not always x is greater than 0, but it's this thing greater than 0. In this case, greater than negative 1. 8 is greater than negative 1, so we're all good. No problems here. And we move on. Does that make sense? Okay, awesome. What about this one? When x is the base, how do I rewrite this? X squared equals 16. How in the world are you going to solve this one? Okay, square root both sides. Sometimes these simple ones, we forget, we think there's something tricky going on, but there is not. Square. So I take the square root of both sides and I get? Thank you, plus minus 4. So we got 2 answers and we're good. What? What's that, Tyler? Yeah, and so in this case, our restriction is x has to be greater than 0 because the base of a logarithm has to be greater than 0. So x equals 4 and x equals negative 4, but this one is inadmissible because it's extraneous. So that's an easy one to miss. Next one. Sometimes these are so easy that people confuse themselves. And I've said this before, but there are subtle differences in how you can solve this. And really, once you're good at it, it's all the same thing, I know. But I'll show different ways, and some people get stuck because there's, well, I don't know if I'm supposed to do it this way or that way. It doesn't matter, but you got to have enough confidence to do it whatever way you want to do it. Yeah, good. So if I'm rewriting this, I would get x cubed equals 10 to the 9. Now, how do I solve for x here? All these little skills that you need to have. This is not supposed to be hard. This is from, I don't know, grade 9 maybe, grade 10, grade 11 for sure. Because this is log base 10. So I just rewrote it in exponential form. Yeah. So how do I solve this? And by the way, we do have a restriction. X cubed has to be greater than 0, which means x has to be greater than 0.
Well, you take the square root, but then we cancel it.
Cube root, thank you very much. So I'm going to write it like this. So I take the cube root, but if you write it as an exponent, it's kind of a nice way to do it because then I got 10 to the 9. You got to do it on both sides, obviously. 3 times a third is 1, so you get x. 9 times a third is 3, so you get 10 cubed, which is 1,000. I'm going to keep moving. Stop me if you have questions, but I am going to kind of go through some of these quickly because we have lots of them to do. There's another way that I could do this one. It's the same. It's not really different. But I could take the 3 out front. Divide both sides by 3. And then I still have to do the same thing where I rewrite and I get x equals 10 to the 3, so x equals 1,000. Some people might like that better. Slightly smaller numbers maybe, I don't know. But again, it really all works out the same. But this is, again, just pointing out the usefulness of this property of taking the 3, bringing it down. In this case, I can divide both sides. I don't know. Take your pick. Whichever one you prefer. And then here's where, again, it comes into like you do have to kind of know how to start and know what to do. In this case, when I have the half out front, I'm going to use that property in reverse to bring it into the exponent. Why did I do that? Don't write this down, but take a look. If I have 2 to the x equals 2 to the 5, that means x equals 5. This is the same. Log base 10 of something equals log base 10 of something else. Those somethings must equal each other. So I have to have a single log on both sides. It's got to be the same base. Log equals log. Therefore, x equals 16 to the 1/2 is the square root of 16. So x equals... Yeah, restriction. X has to be greater than 0 because it was in the argument of the log up here. So I always have to consider my restrictions. So x plus 7 has to be greater than 0, which means x has to be greater than -7. And this is log base 2 of something equals log base 2 of something else. Right? So those things have to be equal. So to me, in this case, you just go, there's 2 ways you can solve this, but I would say this is definitely the easier. How easy was that? As long as you recognize it. If they have the same base and there's a single log, you can't have like a bunch of logs on this side, like this plus this or something, right? Yeah, you would have to do that first though. But you're right, and which we're going to see next. Okay, but I can just say that the arguments are equal. Just like the same property with exponents. What's the other way you could do this? Can I evaluate log base 2 of 4? What is it? It's 2. So I could have also done log base 2 of x plus 7 equals 2. And then rewrite this in exponential form. So this is log equals log. Therefore, this is true. The arguments are equal. This is rewriting in exponential form. But it's the same because I end up with x plus 7 equals 2 to the 2, which is just 4. So I end up back here anyway. So like, it's all the same thing. And if I couldn't evaluate this, you could use the change of base formula, I suppose. But that would get messy, so you'd probably do it the other way. All right, moving along. Looks like this should actually be F. Didn't we already see E? So I am going to get the x by itself and move the log 3 to the other side. And I'm going to bring this 2 into the exponent. And now I have log plus log. So what's the rule that I can use there? We can multiply. So I get log of x. 5 squared is 25. So this is log of 25 times 3, which is 75. My restriction was x has to be greater than 0, so we're good because it's 75. So that's a great example again of like, there aren't real Thursday, but there could be because all of that was just done in our head, all simple calculations. Using this property of adding logs of the same base means you multiply the arguments. That's definitely on the quiz. Some people might multiply this, so 10 times root x, because I can simplify the left side here, right? Or I can move the log of 10 to the other side. Now this is log base 10 of 10, which is 1, but I don't think it helps to evaluate it here. I don't think we want to do that. So I think what we want to do, is, well, we can do our restrictions first. The square root of x is greater than 0. Now the square root of x is always greater than 0. You can't take the square root of something and get a negative number. But what's the restriction on that? Because we can't, yeah, greater than or equal to, because we can't take the square root of a negative. And because we don't, if it was 0, square root of 0 is 0, that still wouldn't work here. This doesn't come up very often, I don't think. But in other words, my restriction ends up being x has to be greater than 0 in this case. So this is log of the square root of x equals log 9 minus log of 10. So I'm going to simplify that. 9 divided by 10, right? Log equals log. Next step. Square both sides.
Do you take the 1/2 outside of the log and then multiply the other side by 2?
Yeah.
And would it not be 18/10?
No,
Oh, it would be
because it's 2 times the log of that.
Yeah,
But then you take that 2, put it back in as the exponent, and you'd end up squaring it.
yeah.
I like that, though. Okay. When is this going to get interesting? There we go. This is sort of the last type of logarithmic equations that we're going to look at. You can see how, like, they're all slightly different. Their solutions look slightly different. You got to kind of know how to do each one of them, right? And be thinking about restrictions and stuff like that. Speaking of restrictions, let's talk about those things. I've got 2, don't I? So x plus 1 has to be greater than 0, which means x is greater than -1. And x minus 3 has to be greater than 0, which means x has to be greater than +3. Now, I want you to think about those 2 restrictions and tell me something about them.
Can it be like in between and then above, below?
Well, you're on the right track at least. And in some cases, I don't think this comes up, but in some cases, you might have to actually do that.
Since x is greater than 3, it has to be greater than -1. Like, one just like.
Yeah, one cancels out the other. So if x has to be greater than -1 and x has to be greater than 3, then x has to be greater than 3. That's the only way that it's going to be greater than both. Often, not always though, often these questions will work out this way where you might have 2 or more restrictions, but one of them kind of tops all the others. And I think it's a good idea to do this. Write them both out and cross out the one you don't want to be looking at, because if you look at it later on by accident, you might make a mistake. And I always circle the one that I actually need, and then I'm good to go. I use the same property as before. I'm adding logs with the same base, so I can multiply the arguments. And then I'm going to rewrite this in exponential form. Now, this is one that some people have trouble with. So let's see if we can make sense of this. Because it's going to look like this. Because if it was log base 5 of a equals 1, a would be 5 to the 1. Base stays the same. That's my exponent equal to a. So this binomial product is my a, in other words. How in the world are we going to solve this one? I don't know. Is this something we're even able to do? What do you think, Lucas? Yeah, I don't think we can do this one. Samir? Yeah, expand, simplify, and then factor or whatever you have to do. Very good. So this is going to be x squared minus 2x minus 3 minus 5, bringing it over equals 0. And remember, our restriction was x has to be, see, if you said x has to be greater than -3, x has to be greater than -1 and greater than 3, in this case, you might be safe, but -2 is not greater than 3, 4 is. So one of them's fine, but this one's extraneous. Okay, I want you to try h on your own. I. If you skip the restrictions, let's look back at them. So x has to be greater than 0, and x minus 6 has to be greater than 0, which means x is greater than 6, which means what can I conclude? Then x has to be greater than 6. So again, we're just rewriting in exponential form here. Equals 4 squared. Base stays the same. 4 to the 2 equals the argument. So this is x squared minus 6x minus 16. Actually squaring 4 and bringing it over. And again, this looks to me like it is factorable. My restriction, x has to be greater than 6. Extraneous. Yep.
Would we know this factor?
No. There it is. So now I, otherwise known as J. If x has to be greater than negative 2 and x has to be greater than negative 3, then x has to be greater than negative 2. Stop for a second and watch. There's two slightly different ways you can solve this. We can evaluate log base 2 of 1. What is it? It's 0. If I do that, then I rewrite in exponential form, and I get this equals 2 to the 0, which is 1. Right? So I can evaluate this, then I have a number, and I would rewrite in logarithmic form. Or I can see that this is log equals log. So I just go x plus 2 times x plus 3, I should have a therefore there, equals 1. Gets you to exactly the same place. The other way takes 2 steps. This is only 1. Some people would say that this is better, but to me it's not really about better. It's what you notice. It's what you feel comfortable with, what you see. If people see they can evaluate and they like to, just because they like doing it that way, by all means. Right, so I would have this. I'll show you. This would be log base 2 of this would equal 0. And then when I rewrote it, I would get 2 to the 0, which is 1. So it's going to work out the same either way. Isaac, I don't think this one factors. B squared minus 4AC. So B squared is 25. 4 times 1 times 5 is 20. 25 minus 20 is 5. Can't factor. Move on. Quadratic formula, thank you very much. We can still solve it. It's positive. It's solvable, not factorable. Therefore, x equals negative b, which is negative 5, plus minus the square root of 5 squared minus 4 times 1 times 5 over 2a, 2 times 1, which is negative 5 plus minus the square root of 5 over 2. And when I do both of these on my calculator, if I can find my calculator, negative 5 plus root 5 over 2. The instructions don't say it. It'll probably would tell you round to 4 decimal places where necessary or exact answers only. Like it'll probably say that. If exact answers only, then there's your answers. But we need to see how these fit in our restrictions. So I still need to do it. And this one works out to negative 1.38. And then the other one, when I subtract, gives me negative 3.62. And my restriction was x has to be greater than negative 2. So this one's not, but the other one is. Any questions? We got one more. I'm going to let you try it on your own. It's a little bit different. I want you to think about it. There's a couple of different ways you can solve this one as well.